Hello everyone, my name is Leonardo Babun and I will present today the paper Real-Time Analysis of Privacy and Aware IoT Applications. This project is a collaboration effort between researchers from the Cyber Systems Security Lab at Florida International University and other colleagues from Purdue and Penn State University. In this project, we are introducing IoT Watch, a privacy analysis tool that uncovers how IoT apps handle and share sensitive information, potentially exposing the user's privacy. The IoT Watch considers the privacy preference from IoT users and applies natural language processing to classify IoT data into privacy labels that are easy to understand by the user. The outline of this presentation is as follows. First, we will overview the main privacy challenges in IoT that we target in this paper. Then, we will present the trend model and the main results from a privacy survey that we performed with real IoT users. The survey aimed to uncover privacy expectations and concerns of users of IoT applications. We will continue the presentation with an overview of IoT Watch architecture, detailing the source code analysis and implementation of the tools, the runtime analysis, and the NLP model that we use to classify information extracted from the apps into specific privacy labels. Finally, we will discuss our evaluation results and finish the presentation with the conclusions. There are 4 privacy challenges in IoT that we target in this work. We use a representation of a real IoT application to explain these challenges. First, the description block of an IoT app not always informs the user about the app functionality or the way they use the data collected from devices and the user. In fact, we found that 25% of the analyzed app didn't have any form of description block in it. Second, we observed that even though the user is required to grant permissions to access the IoT data handled by the apps, the user is not always the one defining the recipient of the app information and notifications. For instance, in the specific case of internet calls used to send data to external servers, the developers define the data recipients in almost all the cases, and the user is never informed. Also, we observe cases where this information is sent out from the application to the internet in plain text, making the sensitive data available to eavesdroppers. Finally, we found cases of malicious apps where the attacker including functions to leak information to unauthorized parties with malicious endpoints or hardcode recipients. Before IoT Watch, IoT applications didn't have any mechanism to expose these privacy concerns and risks to the IoT user. Based on the previous privacy challenges, we consider the following threats in this work. First, we consider application accessing privacy information without informing the user via an app description block. Then, we consider IoT applications that are capable of leaking information either via dangerous or malicious functions. We also consider apps that hide malicious or unexpected functionality to the user. And finally, we consider apps, both benign or malicious, that do not properly protect the information they share with external servers. Our main goal in this work is to design a privacy tool capable of translating the app's privacy behavior into simple privacy labels that the user can understand. Then, with this information, the user should be capable of making an informed decision and reject the apps that do not comply with the privacy preferences. In order to do that, we want to consider the privacy concern of users with IoT systems. We perform a privacy survey and collect information from 112 participants that use IoT systems. In this survey, we included questions covering the participant demographics, their privacy concern with IoT systems, and their point of view regarding the need for privacy analysis tools in IoT. The survey results demonstrate that the user of IoT system is, in general, concerned with the use of the privacy information. However, we also noticed that there is no clear consensus on what kind of data and information should be considered private. There was a general agreement on the need of a user-friendly privacy analysis tool. However, the participants want to have the capability of configuring the tool so it can be adapted to their own privacy preferences. Finally, the participants welcome the idea of receiving notifications that uncover what the IoT apps do with the sensitive data in real time. To address the privacy challenges of IoT applications while covering the privacy expectation of users, we propose IoT Watch. a dynamic tool that uncovers privacy risks from IoT applications in real time. There are three main steps included in the IoT watch analysis. First, at instrumentation time, the tool analyzes the IoT applications and modifies the source code to enable the collection of privacy-related information. Also, our instrumentation step permits the implementation of a notification system that informs the user our findings. Finally, we also instrument the IoT applications to offer an additional interface that the user can utilize to select the privacy preference with the app and create a privacy profile. Such a profile, which includes the type of information that the user considers as privacy sensitive, is defined by the user of an IoT application at install time. Finally, at runtime, the IoT watch collects apps data and analyzes it to uncover privacy risks in real time. The analysis includes the classification of IoT data into privacy labels that are easy to understand by the end user. Also, the IoT watch determines if the app information is sent out from the app in plain text. Finally, our tool informs the user about the findings in a form of a privacy notification. The IoT watch must overcome three different technical challenges to support this analysis. The first challenge is that the tool must be capable of performing effective source code analysis to identify code structures that may be related with privacy behavior. Since IoT applications from different platforms can be written with using different programming languages, we propose using a code translator that converts application code into an intermediate representation. From there, our tool extracts the asymmetric syntax tree of an application and analyzes it to identify nodes, calls, or binary expressions that could contain privacy information. IoT Watch focuses on sensitive information leaving the IoT applications. Hence, we focus on source structure that handles data flows from sensitive sources and free functions that implement sync calls. Two specific examples of these sync functions are IoT messages and internet calls. In general, IoT messages are used in the application to send notifications to the user. These notifications may include sensitive information related to the user behavior or location. On the other hand, internet calls are used in the IoT applications to send application data to external servers via HTTP calls. These calls may include sensitive information like device states and IoT system configurations. The second technical challenge of the IoT watch is related with the instrumentation step. Once IoT watch identifies the source code for sensitive information and the functions used to share this data, it must modify the original source code of an application to enable collecting the privacy-relevant information. Specifically, our tool collects information defined by the developer, the user, or both, that is used by the app as a recipient of the sensitive information. Also, our tool collects the content of the application sync calls to uncover the type of sensitive information handled by the app. The instrumentation step for IoT Watch also provides support for additional functionality. On the one hand, the instrumentation step permits creating a user interface that can be used to select the user privacy preference and create the privacy profile. As an example, in the figure to the right, the user selects and informs the IoT watch that she wants to track whether the application handles data related with the device information and the location. On the other hand, the instrumentation of IoT applications also permits implementing notification mechanisms that our tool can use to inform the user regarding its findings in real time. For instance, in the figure, the user selects to receive notifications every time the app executes suspicious or dangerous internet communications that contain data related with the location and device information. Finally, the IoT watch must be capable of translating the content of an application communications into a language that the user can understand. For this, and by using the result from our privacy survey, we define four specific privacy labels that cover information related with the IoT devices, the user and device location, the user behavior, and the daytime information embedded into IoT messages and calls. IoT Watch uses natural language processing to classify app communication content into these four privacy labels. Then, these privacy levels are compared with the user privacy profile, and if a match is found, the tool informs the user with a privacy notification. The table to the left provides specific example of a real communication content that we define as a privacy string and the corresponding privacy label. As you can see, we consider that the message the thermostat is turned on may leak information related with the devices, and the message door is not opening since the car was not present at home less than 15 seconds ago might leak information related with the devices, which is the door, the location at home, and the date time, which happened 15 seconds ago. Similar type of information, if leaked, can be used by a malicious actor to infer that the house is empty or that the door was left open. The figure to the right uh, shows some examples of notifications received by the users of IoT Watch. These notifications reflect on the user privacy preference and profile. For instance, in the first case, IoT Watch informed the user that a communication containing information related to the location was identified by the tool. As you can see, the location was one of the privacy levels included in the user privacy profile. In the second example, IoT Watch informed the user that a communication was sent to the internet in plain text, which also matches the desire of the user to be notified every time an insecure internet communication happens. We use natural language processing techniques to convert application data into privacy labels. We first tried training the NLP model with corpora data extracted from known general knowledge databases. However, our first classification attempts achieved very low accuracy. We analyzed these initial results and conclude that the IoT strings extracted from the applications are different from the general knowledge corpora in very specific ways. For instance, we noticed that the IoT strings are short and don't have a very well-defined semantic structure. Also, we realized that regarding their size, which is normally a few words, they contain a high amount of information. We then create an analytic corpus with data extracted from real IoT applications and use this dataset to train our NLP model. In total, we extract 2014 different IoT strings covering the 4 privacy levels from 380 different IoT applications. With this new IoT corpus, we were able to improve our classification results. In total, we extract data from 540 different SmartThings applications to implement and evaluate IoT Watch. From the previous slide, we learned that information extracted from 380 of those apps was used to train and test an NLP model. Then, the remaining 160 applications were used to evaluate the IoT Watch performance. Out of the total applications used in evaluation, 120 applications were benign and 40 applications were collected from repositories containing malicious applications. We evaluate the average accuracy, recall, precision, and specificity of our tool in converting IoT privacy data into privacy labels. Also, we perform data analysis for different decision thresholds. In general, our results demonstrate that NLP can be used to effectively convert data handled by IoT applications into privacy labels that are easy to understand by the regular user. Specifically, our tool achieves the highest accuracy while converting data that contain information related to location, and obtaining the lowest classification accuracy with information related with daytime. Finally, our model achieved the best result from a classification threshold of 0.4. We also evaluated how the IoT apps included in this work violated the privacy expectation of users. In the case of sensitive data being shared via IoT messages, we found that no benign applications leaking information. However, we found 29 data leaks from a total of 58 messages extracted from the 40 malicious applications. In the case of internet communications, we found 11 leaks from 120 apps and 22 leaks from 40 malicious applications. Finally, we identified 6 applications, 3 benign and 3 malicious, that sent the data over the internet in clear text. As a conclusion for this work, we present IoT Watch, a runtime analysis tool used to evaluate privacy and security risks from IoT applications. IoT Watch successfully performs source code analysis and implementation to collect data and enable privacy analysis from IoT applications using NLP. IoT Watch analyzed 540 different smarting applications and effectively identified data leaks and privacy concerns from the applications in 100% of the cases. Additionally, we were able to classify privacy-related data flows in over 94% of the cases. Finally, IoT Watch performance yield minimal overhead to the IoT applications and systems. Thank you so much for your time and for attending this presentation. Please feel free to use my contact information included here to reach out and ask additional questions regarding this work.